Welcome back. In my previous video, I have discussed about uniform convergence and pointwise convergence of sequence of function. Today I will discuss new topic, compact set. This is very important. Analysis, topology, metric space. Compact set is very important. And actually today's goal of this lecture is, today I will see at first what is the compact set, then I will say compact set, this idea how depends on to find the uniform continuity of sequence of function, because today's goal of this lecture is sequence of function. So I will at first discuss what is the compact set, then I will define how compact set depends on uniform continuity of sequence of function. But at first, as a review, at first I will define one nice sequence of function. Then I will discuss this concept. Let's see the example. First example, consider domain equal to R plus and sequence of function defined from R to R such that fnx equal to x over n if x lies between 0 to 0 less than equal to x less than equal to n and 1 when x strictly greater than n. Then I will see at first the sequence of function fn converges pointwise to the function fx equal to 0, but this convergence is not uniform. Here R plus means obviously the positive real number. At first, try to ownself this sequence of function, try to draw ownself, then you will understand this sequence of function properly. Let's see the graph of this sequence of function. Here the picture is very interesting. f1x equal to x when x lies between open interval 0 to 1 and 1 when x strictly greater than 1. Then the picture would be such type 1 y equal to x when lies between 0 to 1 and when x greater than 1, then the graph would be such type. This is the f1x and f2x would be x over 2 when x lies between 0 to 2 and 1 when x strictly greater than 2. So f2x would be, here the slope is 1 over 2 x over 2 here, then when x greater than 2, then this is 1, okay, and f3x would be x over 3 when x lies between 0 to 3 and 1 when x strictly greater than 3. Then the graph would be, here x over 2 3 and then the graph is 1. Have you understood this graph? Similarly, f4x would be x at first x over 4, then this would be 1. I hope my all viewers have understood this graph. That means this is x over 2, this is x over 3, this is x over 4. Similarly, if here the large n, then this would be x over n, then after this would be 1. Have you understood this picture? I hope my all viewers have understood this picture. Now I will say this sequence of function converges pointwise to the function fx equal to 0. And I will prove this convergence by sandwich theorem, notice here all fnx lies between 0 and x over n. Okay, and since limit n tends to infinity, x over n equal to 0, that means obviously fnx converges to 0 as n tends to infinity by the sandwich theorem. Therefore, fx equal to actually the 0 function. That means this sequence of function converges to fx equal to 0 function, and this convergence is pointwise, but this convergence is not uniform, because if we consider this epsilon neighborhood 1 over 5 to minus 1 over 5, then all sequence of function fnx does not lies between in this interval. Okay, notice the graph, because if the sequence of function converges uniformly, then the definition is after some steps the all sequence of function lie in this neighborhood. But we consider this ball, here the radius is 1 over 5 and the center is 0, then all fnx after some steps, means after some capital N, does not lie in this neighborhood. So this convergence is not uniform convergent. For this bat epsilon, we can tell this sequence of function not uniform convergent. We all of us know the definition of uniform convergence of sequence of function. Sequence of function converges uniformly. This is true for each epsilon. For each epsilon, after some steps, all the function lie in this neighborhood. But here I have got one particular epsilon, and for this bat epsilon, we can tell this sequence of function does not converges uniformly, but converges pointwise to the function 0. Have you understood? I hope my all viewers have understood this concept clearly. Okay? Oh well. Now I will say our main goal of this lecture, compact set. To find compact set, at first I will introduce open cover. What is open cover? And open cover S is family of open set UI such that S contain union of this open set UI. Now our question, which of the following is an open cover of the real number? Option 1, the set containing n, n plus 1 where n belongs to integer. Say this n, n plus 1 means this type of interval, but this whole interval does not contain r. So this is not open cover of the real number r. Now the set containing minus n, n where n belongs to integer, and this is cover such type minus 1, 1, minus 2, 2, minus 3, 3. Obviously this cover whole real number, so this is be the open cover. Here third set is set containing x minus 2, x plus 2 where x belongs to r. The set is such type, here x and here x minus 2 and here x plus 2. This set contain obviously infinitely many element of real number, so this is be the open cover. Option 4, 1 over n, n where n belongs to natural number. this is not be open covered because this set does not contain negative number, only contain the positive interval. So this is not be open cover. So in real number only open cover is such type. Okay. This is the concept of open covers. Now I will see what is the subcover. What is subcover? A finite subcover of some open cover is just choice of finitely many set which still cover the set A. That means finite subcover means some open cover which just choice of finitely many set which still cover it. And this is something possible, sometimes possible and sometimes not possible. As for example, consider the set A equal to close 0 open infinity. Such type of set. And consider an open cover n minus 1 comma n plus 1. That means O0 would be minus 1 comma 1. This is O0. And O1 would be 0 comma 1. That means this is O1. O2 would be 1 comma 3. O3 would be 2 comma 4. O4 would be 3 comma 5, so on. That means this type of interval, and this is obviously cover, this open cover obviously cover whole interval 0 infinity, but there exists no finite subcover which cover whole set A equal to open interval 0 infinity. Have you understood? Okay. Now consider the set A equal to 0 comma 20 and consider same open cover here also n minus 1 comma n plus 1. Then O0, O1 up to O20 be the finite subcover of this set A. So this cover has a finite subcover. I hope my all viewers have understood what is the finite subcover. That means when a set be unbounded, then this set cannot have any finite subcover. Have you understood this concept? Okay. Now I will see the definition of compactness. A set is compact if every cover of the set S has a finite subcover. That means when every cover of the set has a finite subcover, then we can tell the set S is, here I have considered the set as S, the set S is compact. Have you understood this concept? Okay. Now, as for an example, consider the open interval 0, 1. Then my question, which of the following cover, here I have considered 3 cover, which of the following cover be the, which of the following cover has a finite subcover? For this, at first cover is look like 0, 1, 0, half, half 1. And since this contain finite cover, so always there exists finite subcover. And notice second, 1 over n comma 1 where n greater than equal to 2. And here as n tends to infinity, obviously this tends to 0. And obviously this covered the whole interval 0, 1. But here we cannot get any finite subcover which cover the open interval 0, 1 if we take this cover. Have you understood? But notice the option 3, here I have considered x minus 1 over 5, comma x plus 1 over 5, where x lies between open interval 0, 1. Have you understood this set? Have you understood? Here x be the center and the radius is 1/5. That means here the ball is look like center is x and length the radius is 1/5. Such type of ball whose has fixed radius. So obviously for this open cover there exist finitely many subcover which cover this open interval 0, 1, because here the length of this ball be fixed. But open interval 0, 1 not be compact because for this cover, see the definition here has indicate every cover of the set S has a finite subcover. For this cover we cannot tell the open interval 0, 1 is a compact set. Now consider the set S equal to singleton set 0 union the set containing 1/n such that n belongs to natural number. I will say is this set is compact or not. This is very interesting set. We all of us know 1/n tends to 0 as n tends to infinity. That means actually this set contain all the set 1/n and the limit point singleton set 0. That means this set contain limit point. So obviously this set be closed. Since we have to prove the set S is compact, so consider U alpha where alpha belongs to real number be the cover, open cover of the set S. And we have to prove there exists finite subcover which is also covered the set S. Since U alpha be the open cover of S I have considered it, then consider one ball U1 which be the covered by the 0, by the point 0. Okay, and here the set 1/n, since limit n tends to infinity 1/n equal to 0. That means by the definition of limit we all of us know after big stress all the sequence tends to 0. So obviously the singleton set 0 union 1/k such that k strictly greater than n contain the set S. Contain the open ball U1. That means infinitely many points lies in the open ball U1. That means this set contain infinitely many elements, so there exist only finite element, and finite element always covered by finite open interval. So here every open cover has a finite subcover. So obviously this set is compact set. And if any set which contain the limit point, this type of set always would be compact. And I hope my all viewers have understood why this is compact. There exists a nice theorem. If any set S which is subset of R would be compact, then obviously this set S is closed and bounded. Have you understood this concept? And why any compact set in R is closed and bounded? This proof I will prove in my next video. Today I will discuss actually the sequence of function. Today I will discuss how the idea of compactness is will use to find the uniform continuity of sequence of function. This proof I will prove in my next lecture. And there exists another nice theorem, Heine-Borel theorem. This theorem states that for a subset S which contain the real number, then following three conditions are equivalent. Condition 1, S is compact imply S is closed and bounded, and 3, any open cover S has a finite subcover. Have you understood? These three conditions are equivalent. The given set be the subset of real number. We will see our main goal of this lecture. I will see one nice theorem. Here I will see how compactness will use to define one sequence of function be uniformly convergent or not. Here the theorem is Denis theorem, and the concept is consider a sequence of function which is defined from the set A to R and which is actually the continuous sequence of function. First, here Fn converges to F pointwise, and these fx always would be continuous for all x belongs to A. This is the first condition. Second, either Fn plus 1 less than equal to Fnx or Fn plus 1 greater than equal to Fnx. That means the sequence of function increasing or decreasing, and this is true for all x belongs to A, where A is obviously the closed and bounded set, means obviously the set A is compact. Then we can tell the sequence Fn uniformly convergent on the set capital A. Have you understood this concept? Okay. This proof also I will see in my next video. Today I will see one example about this theorem. See one example as a use of this theorem. Here given Fnx equal to x to the power n, where x lies between in this interval, and notice here the interval is compact, means closed and bounded. We have to prove Fn converges uniformly on this interval. That means here we have to prove all condition of Denis theorem, and here the Denis theorem is applicable because the interval is closed and bounded. Obviously this sequence of function x to the power n, we all of us know in this interval this is converges to 0, which is obviously continuous function, and this converges is pointwise. Now Fn plus 1 minus Fn means this is equal to x to the power n plus 1 minus x to the power n, which is equal to x to the power n times x minus 1. And since x lies between close 0, 0.9995, so in this interval obviously Fn plus 1 minus Fn would be strictly less than 0. That means that imply Fn plus 1 less than Fn for all x belongs to in this interval 0, 0.9995. So obviously since Fn plus 1 less than Fn, that means Fn is decreasing sequence. Okay, that means all condition of Denis theorem has satisfied here. So by Denis theorem we can tell Fn converges to, Fn means x to the power n converges to 0 uniformly. Okay, I hope my all viewers have understood what is the statement of Denis theorem. In my next video, I will prove this theorem again, because this concept is very important for competitive exam. Okay? Today I will stop here. In my next video, I will discuss this concept elaborately. But at first, I will highly recommend you please see today's video with pay attention. See you soon. Stay safe and stay positive always. Thank you so much.